topic is about multiplication of unsigned numbers. So before entering into how we can calculate the multiplication of a binary numbers, multiplication generally takes place in a decimal system. Here the 53 is multiplied with 28. So generally we call 53 as multiplicand. The first number is called a multiplicand and the second number is called a multiplier. So multiplication starts from the units place of a multiplier. So here we have in units place 8. 8 is multiplied with each bit of a multiplicand and the product, partial product is written like this. And tens place we have a multiplicand multiplier bit 2, which is again multiplied with multiplicand and its partial product is written in a shifted position. We shifted one place towards the left and will add this product to the partial product that we calculated earlier. So now the entire multiplication value is we get by adding the each bit position. So this is generally what happens in a multiplication of a decimal numbers. So we have one more example here. If we have more than two numbers, if we multiply, so first units place digit is multiplied with multiplicand and we keep the partial product, and for the tens place we shift the answer partial product towards one position left side, and if it is third one we again shift the partial product towards the left. So we keep on adding the partial products one bit position left side. So the same technique can be used in multiplication of unsigned binary numbers. So here we have a multiplicand 13 and a multiplier 11. So the binary equivalent of 13 is 1101 and binary equivalent of 11 is 1011. So multiplication of a decimal numbers, we have so many possible numbers. The numbers range from 0 to 9. But whereas in a binary numbers we have only two possible values, either it could be 0 or 1. So if we have a multiplier bit 1, then we'll add the multiplicand to the result. If we have a 0, we'll just shift the positions. So in this example we have 1101 in the multiplier position. The first bit is 1, so we'll just simply add the multiplicand value to the partial product. And the second bit is again 1, so we add multiplicand bit in a shifted position. So we move the partial product towards left side and we'll add this to the first product. And if we have a 0 bit in the multiplier, we'll simply shift. We can simply shift, or you can add the 0 value. And again the multiplier bit is 1. We'll shift the value and add the multiplicand. So based on the bit of a multiplier, we shift and add the multiplier. About the multiplication of two unsigned numbers, the same logic is implemented in array multiplier. Here we have multiplicand in 4 bits register M0, M1, M2 and M3, and we have a multiplier in a register multiplier which is represented as Q0, Q1, Q2 and Q3. Okay, so the same logic that we have discussed earlier is also used in array multiplier. These 3 bits can be added through one full adder. Here in the least significant bit of a final product, we have only bit 1, and which is generally added with a 0. So we require one full adder here. In the is represented using this full adder symbol. Here each square is represented as a full adder which can able to add 3 bits. So initially the partial product is all 0, 0, 0, 0, 0. In the previous example, what we are adding? We are adding 1 with a 0. So here we require one full adder. This full adder can be either added with M0 bit or 0 value. Second position we get the bit at final product by adding 0 and 1. So here we require two full adders. then and one is the result will be added again with the one with second full adder. So that is why in the second bit position we have two full adders, and the third bit position it can be 3-bit full adder. So in the similar way, so each bit is added to the final product by having different full adders. So 4-bit register, we require 4 full adders for getting the first initial product, and remaining 4 full adders for getting the partial product to 2, and this partial product will be added to the first product in a shifted position. So that is why m0 will be added to the in cross lined position. Okay, so this is the internal structure of the full adder. So this the inputs of this full adder are m0 or 0, q0 or 0, and the result of this full adder is p0. So this is the internal structure. It contains one AND gate. AND gate is performed based on mj and qj. So what here in the previous example we are adding the full multiplicand only when the multiplier bit is 1. So that is what here happened. With the based on the multiplier bit we'll add m0 value. If multiplier bit is 0, we'll add 0 to the full adder. So that is why this q0 is given to the AND gate, and based on the q0 value, so we'll add either mj value or 0 to the final product. So this is the general implementation of array multiplier. So what is the disadvantage of array multiplier? Because if it is a 4-bit register, so each partial product requires 4 full adders. Totally, for getting the final product we require 4 into 4 16 full adders. So what is the case if we use 32-bit register? So 32 into 32, so we require so many number of full adders that we need to choose an alternative way of multiplication. So that is sequential circuit multiplier. The sequential circuit multiplier works in a similar way like array multiplier. Instead of using multiple full adders, we are using one n-bit adder. One n-bit adder here. So that same n-bit adder is repeatedly used by the shift registers to make same activity that these all full adders are doing. Okay, so this is the circuit diagram or register configuration of sequential circuit multiplier. So this sequential circuit diagram contains 3 types of register: register A and register Q for multiplier, and register M for multiplicand, and a carry bit, and also a full adder, n-bit adder. So n-bit adder is nothing but it contains n number of full adders. And we have one more control sequencer here. The logic behind this multiplication is same, but they just used a single full adder. Initially, so they used a shift register CAQ. So A initially contains all zeros and Q contains multiplier bit, and multiplicand bit is selected through this multiplexer. Resultant register which contains 2n number of bits. So that is why we will have a final product both in A and Q. So the least significant bit of Q will be here, so which is going to control the control sequencer. So if Q0 is 1, what I have to do? I have to add the multiplier. So we choose whether to add this multiplicand to the adder or not through the Q0 bit. So this Q0 bit is added as a control to this multiplexer. If it is chosen 0, then it will only add, it will not add it will add 0 to the n-bit adder. If it is Q0 is 1, then it will add the multiplicand to the already presented partial product which is in A to the multiplicand. Let us how the sequential circuit multiplier works to calculate the multiplication of a number. A is 0 and carry is 0. M contains multiplicand and Q contains multiplier. So we generally keep on adding the multiplier based on least significant bit of a Q. So if it is 1, we have to add the multiplicand to the partial product. Q naught is not 1, we'll don't add, we'll just shift the value. If Q naught is 1, we'll add multiplicand and we'll shift the answer partial product. If it is 0, we'll just shift the product. We keep on doing this till entire multiplier bits are checked. We will have one more loop here till all the elements of a multiplier bit are completed. The result after completing n number of times, where n is the number of bits of a multiplier. So we'll see example now. Suppose my multiplier for the previous example, which is 13, multiplicand is 13, 1 1 0 1, multiplier is 11, 1 0 1 1. So initially C will be 0, A will be all zeros, and Q is multiplier 1 0 1 1. What is the least significant bit of Q? Which is 1. So if it is 1, so what I have to do? I have to add multiplicand to the A. A is 0 0 0 0 and M value is 1 1 0 1. If we add these two, we'll get 1 1 0 1. And I wrote all the numbers 0 and the sum of these two 1 1 0 1 and the same value 1 0 1 1. I added the M value and I shift the value. Shift A and Q. Carry will come to the A to the next position, 1 to the next, 0 to the next position, 1 to the 1 here, 1 to this place, 0 to this and 1 to this, and this bit is neglected. So and we decrement the first one bit is completed. So for one time, so because we have 4 number of digits in multiplier, we have to repeat the loop for 4 times. So one time is completed. So now what is the least significant bit of Q? Is 1. So if it is 1, we have to add the M value and shift. Let's add 1 1 0 1 to this value. So if we add 1 and 0, I'll get 1. 1 and 0, 1. 1 and 1, this one and this one. 1 and 1, 0 and 1. 1 and 1, 1 plus 0 plus the carry 1 is 0. 1 0. 1 here, 0 here, 1 here. So this is the final product after adding the M value to the this value. Now we have to shift the values. I copied these to this multiplier bit here and now shift the value. Carry to this place, 0 0 1 1 1 1 here, 0 here, and this one is neglected. So now what is the least significant bit of a Q? Q is 0 and I have to decrement the value. It is second loop. So for every shift we calculate it as a one cycle. 0 if it is 0, 0 if it is 0, we don't add, we'll just shift the values. So I just copied entire line here and we now shifting 0 here, 1 here, 0 0 1 1 1 1. So again after shifting the third loop is completed. Next, check the condition. So what is present in the list is Q naught. Q naught value is 1. For Q naught value is 1, we have to add the M value and shift. Add M value 1 plus 0, 1, 0 plus 0, 0, 1 plus 1, 1 0 0 here, 1 carry from here, 1 plus 0 plus carry, 1 0 0 here, 1 here. Again we need to perform shift operation, shift this one here, this. So every bit of this digit are shifted to right. So we have completed our fourth loop. Because I have only 4 digits in my queue, this loop has to be executed for 4 times. So my final product will be this one, both combination of A and Q, which is a negative number. So which is equivalent to 143. The problem with the sequential circuit multiplier is we cannot perform for a negative numbers.